Hello and welcome to lab number 5, titled Finding the Speed of Light in an Acrylic Block. In this lab we are going to use a specific phenomenon that is associated to the light, so-called refraction or bending, to figure out the speed of light. Before we do that, quick explanation. We are considering light as an electromagnetic wave with a specific speed. We know that the speed of light is changing as light is moving from one medium into another. The speed of light in air or vacuum is about 3 × 10⁸ meters per second, and when the light passes into a different medium than air or vacuum, its speed is going to be reduced, and the factor that shows how much speed of light is being reduced is so-called index of refraction. So in this lab we are going to use an optical block made out of acrylic, which is a medium in which obviously the light is gonna reduce its speed. So we want to use so-called Snells Law of refraction and phenomenon called the refraction or bending to figure out the index of refraction of the acrylic that the block is made out of. And by calculating the index of refraction of acrylic, we will be able to calculate the speed of light in acrylic, and that's going to be the goal of this lab. We are going to use the following equipment in this lab. Laser diode module. I'm using here an affordable red laser diode module. You can use any other laser pointer class 1. And then we're going to use the optical block, protractor, pencil, and a white sheet of paper that is going to be taped down to your workbench. The first step in completing this lab is to tape the white sheet of paper down, and then also to tape down your laser and turn it on. So you would want to position the laser along the long side of the paper in order to provide for enough space to complete the experiment. And once your laser diode module has been positioned, you're also going to position the optical block. You want to make sure to hold this optical block for its edges and keep it clean and clean of any kind of dirt and fingerprints. If there's any fingerprints on your optical block, you want to make sure to clean it using proper cleaning procedure. And as a next step, you're gonna position this optical block, and then you can immediately see that when the light goes through this optical block, you are creating a few effects here, one being a reflection off of the front and back surface of the optical block, as well as bending of the light or optical refraction. So we want to position this optical block at a certain angle so that we can observe the light refraction or bending of the light, which is what is going to be used as the primary phenomenon here to find the speed of light in the optical block. Once you properly position the optical block to observe the bending of the light or light refraction, we are going to hold this optical block and make a footprint of it on a sheet of paper as a first step. And then as a second step, while holding the optical block, you want to trace the beam coming out of your laser before it hits the optical block, and then finally as it exits the optical block over on the other side. So to do that, I'm gonna use the pencil to mark the dot, so you can basically move the pencil and find when the laser beam hits your pencil, the tip of your pencil, that's going to be where you're going to position the dot. And you would want to make at least 2 dots in order to be able to make a straight line. Here's the second one. And then I'm going to go over on the other side and also find the beam that's exiting the optical block, which is going to be our refracted light beam. So we have one here, and then one more here. Once you are done with this step, you can remove the optical block to move it out of your way, and then also you can turn off your laser pointer, and then you're going to perform the rest of the lab, which is going to be the measurements. Now that we move the laser pointer and optical block out of our way, we are going to improve the footprint of the optical block on our sheet of paper. And then we are also going to connect the marked dots. So we have 2 dots on this side here. So this line here represents the incident light ray that came out of the laser diode module. And then over on the other side, we have 2 dots to connect. And these 2 dots over on the other side represents the beam that's been created by bending the light as it passed through the optical block. You can immediately observe that the incident light beam and refracted light beam, they are not positioned along the same line. They're supposed to be parallel to each other. However, due to the bending of the light, we have a slight shift of the refracted beam compared to the path of the incident light beam. If you would extend the incident light beam, you can see that there is a significant shift of the refracted beam relative to the path of the incident beam. As already mentioned at the beginning of this lab, we are going to observe the phenomenon of light refraction here. There's 2 distinct phenomena that are taking place here. At this front surface, we have a light refraction, so I'm gonna label this point here as a point A, where refraction of light takes place as the light is passing from the air into the optical block. And then over on the other side, at the point B, we are going to have a second light refraction where the light beam is passing from the optical block into the air. We can also connect points A and B to establish the beam path through the optical block. So I'm going to connect the points A and B here. So we are going to label this light ray here as an incident. And then this light ray that's in the optical block, we're going to call it a primary refracted ray. And over on the other side, we are going to have a light ray that's been created after the second refraction. So we're going to call it secondary light ray, refracted light ray. In order to calculate the speed of light through the optical block, we need to calculate the index of refraction of the optical block, and we are going to do that using Snell's law of refraction. So in order to use the Snell's law of refraction, we have to establish certain angles that are going to be used in a formula that's known as a Snell's law of refraction. So the first step in doing that is to establish the reference line or axis that's perpendicular to the surface at which optical refraction takes place. So we have, as already mentioned, 2 points where refraction took place, the point A and point B. So we are going to select the point A, and as an exercise that you may complete on your own, you may do a similar calculation for the point B to confirm the results that we calculated at the point A. So at point A, we are going to create a reference line or axis. So that axis has to be perpendicular or at right angle relative to this surface at which refraction took place. So we are going to use the protractor to do that. So we are going to position the center of the protractor and then align this reference line on the protractor with the surface of the surface at which the refraction took place. We are going to mark 90 degree over on the other side, and we are going to establish this line. I'm going to make it as a dotted line. That is going to be our reference line. I'm also going to extend it into the optical block because over on the other side we'll be doing the measurement of so-called the refracted angle. Now we can identify two angles of interest here. The first angle is the angle that incident light ray makes with our reference line. So that is going to be this angle here. We are going to call that angle theta 1. And then over on the other side, we are going to establish the angle that primary refracted ray makes with our reference line, and that is going to be this angle here that we are going to call refracted angle, or angle theta 2. Now we are going to measure both of these angles using a protractor. So again, the way you use the protractor, you're going to use this point here, the 0 point, the origin of the coordinate system, position it along the reference line. So as you can see here, the line on your protractor has been aligned with our reference line, and over on the other side we see where our reference line is coming out. So we are measuring from here this angle all the way to our incident light ray. So you're going to use the scale. There's two scales here on the protractor, one that starts at 180, that's the one that you don't want to use. You want to use the scale that starts with 0, so 0, 10, 20, 30, 40, and then you have 41, 2, 3, 4, 5, 6. So we are talking about an angle of about 46 degrees. So our theta 1, our incident angle, is going to be equal to 46 degrees. We are now going to perform the measurement of the refracted angle theta 2. So the same way, you're positioning the 0 point on your protractor to the origin of the angle that you're trying to measure. As you can see here, the 0 line is aligned with our reference line, and then we're going to measure this angle all the way up to there. So again, you're using the scale that starts with a 0. So it's 10, 20, around 30 degrees. So our theta 2 is going to be 30 degrees. So the formula for the Snells law of refraction is written here right now. N1 sine theta 1 is equal to N2 times sine of theta 2, where N1 represents the index of refraction of the first medium. In our case, that's going to be air. So we know that our N1 is going to be equal to 1. N2 is the index of refraction of the optical block medium, so we can label this medium here as N2. That's our unknown index of refraction that we need to calculate. And then angles theta 1 and theta 2 are the two angles that we just measured, incident angle and the refracted angle. So now we are going to substitute 1 for N1 times sine of 46 degrees is equal to N2 times sine of 30 degrees. And as a next step, we are going to calculate these two trigonometric functions. So we have 46 degrees sine equal to 0.719 equal to N2 times 30 degrees sine is going to be half. And then from here we can calculate N2 as 0.719 over 0.5 gives us the value for the index of refraction of the medium that optical block is made out of. So 0.719 over 0.5 equal to 1.438. So what you can observe here is that the index of refraction of the acrylic block, of our block, is larger than 1. So the material that the block is made out of is optically more dense than air. And another interpretation of this number is that the speed of light in this medium is lower than the speed of light in air. So we know that the speed of light in air is equal to 3 times 10 to the 8 meters per second, or about 186,000 miles per second. This can also be written as 300 million meters per second. And now the speed of light in optical block that's of interest here, that's our goal for this lab, is going to be reduced for index of refraction factor. So the speed of light in optical block is going to be equal to C over N. So again, C represents the speed of light in air, while V represents the speed of light in the block. So here we are going to substitute, so 3 times 10 to the 8 meters per second for C over 1.438. And for this one you can also do the calculation. So we're gonna do just 3 over 1.438 gives us the value of 2.086 rounded times 10 to the 8 meters per second. So what we just calculated represents the speed of light in the optical block. So you can see that speed of light in an optical block has been significantly reduced relative to the speed of light in air. And the last observation that we want to briefly talk about before we conclude this lab is the way how the light is bending when it's moving from one medium into another medium. What you can observe here is that at the point A, we have an incident light ray and we have a refracted light ray. You can see that in this case here, the refracted light ray is bending towards the axis. You can see how this angle here, so it's kind of like you have this direction, right? So this is the direction of the incident light beam, and then the refracted beam is bending towards the axis, towards our dotted line. So once more, here's the incident light beam that would eventually have continued along the same path if we hadn't had the block. Since we had the block, we have a light refraction where the light is bending towards the axis, towards the dotted line. So the light is always going to bend towards the axis if we are moving from a material that's optically less dense into the material that's optically more dense. What do we mean optically less dense or optically more dense? You have to look at the indices of refraction. In this first case, we have index of refraction being equal to 1. And for the second medium, we have index of refraction being equal to 1.438. So we are moving from optically less dense into the optically more dense medium, and that's why the light is bending towards the axis. An opposite phenomenon is taking place at the point B, where we are moving from optically more dense into optically less dense medium. So the first medium in this case here is going to be the optical block medium, and the second medium into which the light is refracting is the air. So here we are moving from optically more dense into optically less dense medium. And you can see here that the light in this case here is bending away from the axis. So I have drawn here the axis at the point B, and you can see here if we are looking at the primary refracted ray, which in this case here plays the role of an incident light ray, It would have continued along this line, however it's bending away from the axis, which is our secondary refracted ray. So here we are observing the effect of light bending away from the axis when the light is moving from optically more dense medium into the optically less dense medium. You're going to see that this effect of bending away from the axis plays an important role in effect that's known as total internal reflection, that's at the core of guiding the light through optical fibers. That is going to be the topic of a different lab.